So welcome to lecture 12. Today we're gonna, so far the last lecture or the last two lectures we've spent time looking at some abstract notions, some spectral theory with the explicit intent of trying to understand the adapted operator to the boundary. So today we're going to start looking at the model problem, which is really looking at the problem on the cylinder. So that's the first thing that we need to understand. So let's start with that. So the model problem. Oops, this happens every time. The model problem. Okay. So recall that we have some operator D and inside this neighborhood U, which we can deform to some R cross partial M, we have that D looks like some sigma T dt plus A plus RT, and we now consider the operator D naught equals to sigma naught dt plus A, and we do this on the infinite cylinder. Which we call Z, which is just going to be Z, which is going to be 0 to infinity cross partial M. Okay, so this is the model operator that we extract because we see the model operator in this expression. Okay, so here we can see that the non-trivial operator here is this operator A. So let's begin with a proposition. Let D be as before, so this is a first order elliptic differential operator, and A any adapted boundary operator. Then the following are true, right? Then the following hold. So first of all, the spectrum of A is discrete. With smooth finite dimensional eigenspaces or generalized eigenspaces. Okay. Second is that we have the existence of some radius as well as some omega, which is less than pi on 2, such that the spectrum of this operator now is contained in a sector, so a closed bisector, union. That's precisely what it. So the question is, what does it mean for the spectrum to be discrete? What it means to be discrete is that it is only point spectrum without any accumulation points, right? So this is what we discussed some time back when we were talking about compact operators and their spectra, and then we were talking about detecting the discreteness of spectra for unbounded operators via the existence of compact resolvents. So discrete spectrum for us always means it's a countable set which is with all points being isolated. So the only point of accumulation is infinity. Okay, so the second remark is, so the second point is that we have some radius and some omega such that the spectrum is contained in this closed bisector union some ball of radius around 0. Okay, so its spectrum is contained in the bisector with an error term of being a ball. The third point is there exists now some constant some finite constant such that for all zeta outside of this S omega union this ball, okay, so for all zeta outside of this this closed sector union a ball bisector, the resolvent estimate holds. Okay. The other point is that there exists Rj, a set Rj, with limit j to minus infinity of Rj equals negative infinity, limit j to positive infinity of Rj is positive infinity, and for all Rj, for each Rj, there exists some omega j pi on 2 such that Arj, which we define to be A minus Rj, is omega r bisectorial and invertible. Okay, so this is the theory, this is the proposition that really somehow furnishes us with the understanding that we really need about the operator A. Okay, so this is not a sequence of real numbers. Okay. Sorry, this is a sequence. Yes, this is a sequence of real numbers. Right? So the RJs are a sequence of real numbers. Of course, the spectrum of A are not real, but the RJs here are real numbers. Yes. Okay. So so this tells us a number of things. So we have discrete spectrum. So really, 4 we expect to be a consequence of 1. Right? So also knowing, of course, 2 and 3, because okay, so maybe we'll see what happens when we prove this. So the first thing we need to do is, so the most important thing that we actually have to show is we have to understand the spectrum of the principal symbol of A. Okay, so first we show that whenever we take some point x on the boundary and some non-zero covector at x, that the spectrum of the endomorphism now, right? So this is x psi intersect R is empty. Okay, so remember that even though the operator D might map between the bundle, so I should say, sorry, in this is really a map that maps from E to F, right? We're not assuming that D is an operator that maps from E to itself. However, remember that this principal symbol of A is a so A is an operator that maps from E to itself. because the principal symbol is the composition of the inverse of the tau direction for E for D and the psi direction. So this is now endomorphism from E back into itself, right? So that's why we can even talk about the spectrum of this endomorphism. So so we do this by contradiction. So suppose for contradiction, there exists some psi that's non-zero, a lambda in R, and V non-zero, such that so lambda V is equal to x psi V, right? Which, as I just mentioned before, this is the same thing as dx tau inverse composed with dx psi of V. Okay? So now we multiply both sides by the symbol in the tau direction. So we have lambda dx tau V is equal to dx x psi V. Okay? And this is now a very important property of, okay, so maybe I'll write this minus is 0, right? I'll write it in this way. So this is a very important property of first order operators, is that in the cotangent variable of the symbol, it's a real linear map, right? So this won't be true if it's a second order operator, but for a first order operator, it's true. So because it's real linear, this is if and only if dx lambda tau minus psi V is 0. Okay? So now that means, so now tau and psi are linearly independent, right? Because the tau is pointing in the conormal direction. So tau and psi are linearly independent. So that means that so that in particular means that tau minus psi is non-zero, right? Okay, so we have a non-zero vector, covector, and we have this equation, but that means that so we've now found a non-zero covector for which and a non-zero V for which the symbol of D is 0. So that means that D is not elliptic, right? So this contradicts the ellipticity of D. Okay, so that's the contradiction. Okay, so that's the first thing. The next thing is so that proves that. So that's the first claim. So maybe this is A. The second thing I want to prove is that the spectrum of a x psi is contained in some sector S omega. Okay, so that's the second claim. So for this, so fix an auxiliary metric G on the boundary, so this is a smooth map. So now using so I should say by continuity of spectra and compactness of the boundary, we have that the union of x in partial m of the spectrum of ax psi normalized by this g. So this, so I'm using the compactness also of the unit sphere bundle, right? So this is now a set that is disjoint. It's compact and disjoint from R. Okay. So that means we have the existence of some omega such that so there's an omega less than pi on 2, in fact, such that the union of x in M spectrum of okay, so maybe I've made a tiny technical error here. So this should really be rotated, right? So the spectrum here, so we've said that it's disjoint from R, so this is I times the spectrum. Okay, so this is I times the spectrum, so we need to rotate it. So this means that I times the spectrum of AX psi on psi partial M is contained in this S omega. Okay. Also now, we have that T maps to X T psi is homogeneous of degree 1. So that means that we can recover all of our covectors by just lines going through through 0 and the cosphere bundle. So that means that now if we take the union of x and then the union of psi, of the spectrum of ax I times ax psi, then this is going to be contained in S omega. Okay? So this is the main important thing to prove, actually. So from this now, I want to assert that 2 and 3, I won't prove this, but this follows from pseudo-differential methods. So it's going to be beyond the scope of our course to really consider these things. And this is in the book of Shubin. S-H-U, Shubin. Oops. S-H-U-B-I-N. Okay? So there is a way of going from understanding where the symbol of an operator sits to understanding where the L2 operator sits, as long as things are compact. Okay, so we're in a compact manifold without boundary, and that's why we can get all of this to work. And of course, we have to have a ball of error, right? So I'll talk about that in a remark right at the end, where this ball of radius r comes from. Okay, because here we've only talked about the principal symbol. Okay. Yes. Can we use all psi for one psi? But this is for all psi. We've normalized the psi here, right? So we've shown, so what have we shown, right? We've shown that the spectrum cannot hit the real line. Okay? Now we have a map here. X maps to the principal symbol of X, and then this psi here, so this assignment here is just from the cosphere bundle, right? The cosphere bundle is compact. Therefore, we have I mean, the spectrum moves continuously when we perturb from, so if we have a perturbation of operators that is yes, so this is for all, so this is for all psi in Tx star of m. But the point is that now we're really looking at the cosphere bundle here, right? So we're using compactness here. We're using the fact that the assignment x psi to this, so really we have to consider elements coming from the cosphere bundle and use the compactness. So we use the compactness and continuity to know that this whole set is compact and disjoint from R. And that's where the omega comes from. Okay. So back to the remainder of the proof. So 2 and 3 now follows from the pseudo-differential methods, and this is in the book of Shubin, so I won't say more than that. So then it amounts to 1. So this follows from 2, right? Because we have, since the resolvent set of this operator is non-zero, and in our last remark, or our remark following in a previous remark, I'll say, right? In previous remark, we showed exactly this, right? That we get discrete spectrum satisfying the conditions we want if we have a differential operator with a non-empty resolvent set. Okay. And so the last point, I'll leave as an exercise. So is it 0.4? Yes. Okay. So let me just now make a remark and draw a picture, right? So why do we go from S omega at the symbol level, at the level of principal symbol to S omega union B RA 0 at L2 level? The previous remark, we showed this. We showed that if we have a, so the question is, what did I write after prior remark? And I just wrote that we showed that if the resolvent set of a differential operator is non-empty, then we always have, on a compact manifold without boundary, we have discrete spectrum. Maybe it wasn't a previous remark, maybe it was actually a corollary or a proposition. I can't remember, sorry. Anyway, back to this remark. So we have at the symbol level, we have that the spectrum of the symbol is contained in this bisector S omega. So why do we now pick up an error term of a ball? So consider this. So let's have a look at two operators. So let's suppose that we start with an operator whose spectrum is in this bisector, right? So suppose that this is the spectrum of A. Now let me consider the operator A and we subtract some R, right? So now we look at the spectrum of A minus R. So let's say R is some number, then we end up with the spectrum looking like this. Right, all we've done is subtracted, I don't know, R from the operator. So now the point is that the principal symbol of AX psi and the principal symbol of A minus R X psi are the same. Okay, so at a principal symbol level, we don't see what happens to lower order terms. So this is precisely why we have to have some ball of radius here, right? So here we still get some angle. So now the angle might be slightly larger. Sorry, let me just, yeah. So the angle here might be slightly larger. Then we need to have some angle, but now we have some error term here, right? So now we have to have some error term here to account for the fact that we have to have a slightly larger angle. Okay, so we have to have this ball of now radius r to account for the lower order terms. And what this theorem is really saying is that the amount that things can move is at most some compact region in the complex plane. Okay, so that's a deep statement, but so I just want to give an indication as to how this is proved, how we go from knowing information at the principal symbol level to knowing things at the level of L2, right? But I won't say more than that. Okay. So in particular, as a consequence of this, right? So I should maybe, so that's the first remark. So what's the second remark that I've left as an exercise? So the second remark is, now we have an operator with discrete spectrum, right? So let's say that this is our bisector, and then these are our spectral points. But it's discrete spectrum, and that means that there are no finite dimensional accumulation points, right? There are no finite accumulation points. So where do these RJs come from? The RJs come from the fact that we can draw lines through the spectrum missing eigenvalues, or the generalized, the eigenvalues, right? So we can always draw such points, and we can draw an infinitely many of them, right? We can move, we can go through this, we can go through the through this region S omega union a ball without ever hitting an eigenvalue. And we can do this out to plus infinity and out to minus infinity. So these are our points Rj. So now what happens is, if we subtract the operator, so if we subtract one of these points Rj, so what does it look like if we subtract a point Rj? So the operator, so this is the operator, this is A, and this is A minus the Rj. So what we have is, we have an operator maybe here with spectrum like this, and of course the point is that now the angle might have to increase. Okay, so the angle might increase, but now we have, now we have a resolvent point at 0. Okay? And because we also have a resolvent point at 0, and the resolvent set is an open set, we know that there's an open ball of resolvent around, right? So because we have an open ball of resolvent, it also means that we can organize things to draw, so the spectrum of the operator really, so the spectrum of the operator now, maybe I shouldn't have drawn it like this. I should have used a different color. So this is the purple. This is where a priori the spectrum is contained. And then we have some ball here where we don't have any spectrum. So we've drawn this line. We know that in some neighborhood of the line we also don't have spectrum. And so what we really end up with then is an operator with spectrum that looks as follows. So we end up with an operator with spectrum like this. Right? So all the spectral points are out here. So in fact it's still, okay, maybe I should have drawn these lines a bit sharper, because it's not really, it doesn't look bisectorial now, right? So this is certainly a region. So the spectrum here of A minus R, so AR, RJ I should say, RJ, Rj. So the spectrum of AR is now in S omega, subtract, so it's even better, so now we can subtract some strip of some radius, right? So there exists some radius, I don't know, some epsilon radius, so I should call this the omega j, minus some strip. Z in C such that the real part of Z is less than some. This is contained in S omega subtract Z in C such that the real part of Z is bounded by epsilon j. Okay. So as a consequence, so what we're going to assume from here on, we assume A is omega bisectorial and invertible. Right? So the point is that the difference now, even if we start with a model operator which has, if we start with a model operator where the operator A is not of this type, we can subtract off the constant to make it into this type, right? And then the error term that we have to control now can get absorbed back into, so remember we had the operator of this form, right? So the point is that given some adapted boundary operator, we can obtain the operator in this form that we wrote originally. So the point is that now if we choose an adapted operator A and we find that it's not of the type that we want, then we can subtract off a constant and the constant gets absorbed into this term RT, right? So we can always organize the model problem to be an operator A which is invertible omega bisectorial without any issues. Okay, so that's a very, very important point. So maybe I should really write this down, right? So, okay, so the third point is from here we assume that it's A bisectorial and invertible. So recall that having fixed an adapted boundary operator A, we obtain D equals sigma t partial t plus A plus RT. So now for some Rj in R, we have A Rj, so ARJ is omega bisectorial, omega j bisectorial, and invertible. So D can now be written as sigma t plus ARJ plus RT minus RJ. Right, so this is minus, okay, sorry, plus RJ. Right, so this is the new remainder term now. Okay, this is what I'm saying. So we can always extract out a model problem where the operator that we're interested in is omega bisectorial, right? So that's an important remark I'll make. Okay, now the next proposition. Okay, so we've understood how we can reduce the model operator to a very, very nice bisectorial and invertible operator. The next yes? Hmm? No. The question is, why can we find the bisector, right? The point is, item number 2 gives us a bisector. Okay? This is saying that we have the original operator already in a bisector. So now if we subtract some number, suddenly the spectrum can't, lie on some line heading out to infinity across an imaginary axis, right? So the reason, yes. So we haven't really, we haven't given a proof for point number 2, right? All I've given a proof for is to show that the spectrum of the principal symbol is in a bisector S omega. Now the point is there is some pseudo-differential magic involved in getting from the spectrum of the principal symbol to the spectrum of the L2 operator, and that I'm not going to cover. I've given a reference for that, which is Shubin, but the idea is that when we have information about the spectrum of the principal symbol of an operator, we can now extract out information about the principal symbol of the L2 operator, but up to some error term, right? That's where the ball comes in, because I've shown here that even if we start with an operator that we know where the spectrum is contained in a bisector, if I subtract off a constant number, then the principal symbols are still going to be equal. But now it's no longer contained in a bisector. It's contained in a bisector union some ball. So the compactness of the underlying manifold is of essential importance here, right? So the spectrum of so the question is, why is the spectrum of the principal symbol, why does it have to be in a bisector? Well, the point is, okay, so maybe I'll make a remark here, okay? So let me make another remark before moving on, because it's important that we understand this. So remark 4. So maybe I should really have focused on this proof a little bit more. So what do we have in the proof? So in the proof, we have that so for all x in M and psi in T, x star M that's non-zero, we have that the spectrum of A, X, psi intersect the real line is empty. Okay, so what's that saying? That's saying that the spectrum of such an operator is always staying away from the real line, right? Well, this is a finite dimensional object. I mean, this is an endomorphism from EX to EX. This is just a matrix, so the spectrum is always finite here. Okay, so it's finite. Now what we do is we consider the map x psi to AX psi, where this is now a map from partial M, and then we're now taking the sphere bundle with respect to the cosphere bundle with respect to this fixed metric that we had, right? So I'm gonna now consider this as a map from there to these matrices, right? So to these endomorphisms. Now this is a map from, so this is a compact space, and this is a continuous map. So because it's a continuous map, the eigenvalues only move continuously. And because they move continuously, and because we have a bound on the distance, we have that this can never intersect the real line, right? It's just the extremum value theorem. And so then we end up with a picture like this. We end up with a picture like the spectrum might be like this of the corresponding thing. Okay? So if we now multiply by I, we rotate this, and then we end up with the spectrum like this. And then we have that the each point, because our considerations were on the cosphere bundle, every point in T star x x of partial M, so on the cotangent bundle, by the homogeneity of order 1 of the principal symbol for a first order differential operator, we could recover everything by drawing lines through here, right? So if we're drawing lines through here, then we have a sector now that is completely free. And this is our omega. Okay. All right. So sorry, I should have maybe spent a bit more time on that. So the second thing that we need to know is the following. Chi plus so recall chi plus minus of zeta. So this is equal to 1 for the plus minus, the real part of zeta is positive and 0 otherwise, right? We've already seen this. So what we want now are spectral projectors, and what we have is the following, right? We have the following proposition. We have that chi plus minus a. So this is A is an adapted boundary operator, omega bisectorial invertible. So for such an operator, then if A is okay, then we have that chi plus minus of A, chi plus minus of A star. These are bounded operators on the Sobolev scales H alpha partial M E for all alpha in R, including the negative ones. Okay? So again, the proof of this takes us out of the realms of what we're going to consider in this subject, but the idea is, so that I'll give an idea. So the idea is, so this is due to Gerd Grub, due to Grub. So she proves that so under the condition that this principal symbol is contained in S omega, these operators are pseudo diff ops of order 0, and this is related to complex powers of operators and stuff that we don't really have time to get into. Okay, so such operators, i.e. pseudo differential operators of order 0, are bounded on all Sobolev scales since the manifold is compact. Okay, so it's just a proof idea. I just want to say the word so you know where to look it up, but that's basically what we have. So this is now bringing us closer to what we discussed last time, right? So we ended last time with a corollary or an example of a differential operator which is bisectorial and invertible, and whose spectral projectors are bounded. Okay, so these are projectors, of course, right? We have a functional calculus. If we square these things, because the functional calculus is well, actually, we don't have a functional calculus yet, but it's not too hard to show that these are projectors because of their definition, right? At the level of the functions, they are idempotents. And they are also mutually, right? So if you multiply the chi plus and the chi minus, they're 0, but if you sum them up together, you get the identity on the entire spectrum of the operator, right? So in some sense, there is an underlying functional calculus here. So the important thing is now this. So with all of this, we arrive at the main thing. So the operators modulus A star, which is also equal to A star, A and A star enjoy an H infinity functional calculus. In particular, the integral 0 to infinity of T alpha modulus A to the power alpha e to the minus T modulus A of u squared dt on T is comparable to u squared for all u in L2 of partial m. Okay? So what's the proof? So we've already mentioned that, so what's modulus A? This is the signum, this is A, signum A. And we have that signum A is equal to chi plus of A minus chi minus of A. And these we know are bounded. Are L2 bounded. So that means that modulus of A is omega sectorial and invertible. So, i.e., the range closure of modulus of A is equal to L2 itself. Right? So then, okay, moreover, we have that the domain of A is equal to the domain of A star, which is H1, because they're differential operators, right? We've already seen, I'm just writing down what we've already seen in the previous example. So by the O'Shea, McIntosh, Namod theorem, obtain required estimate or obtain H infinity functional calculus. So actually invertibility is important here, right? Note, by invertibility, the norm of UH1 is comparable to the norm of A of modulus A, modulus A of U. Well, it's also A of U, right? Without a lower order term. And because A is invertible, so is A adjoint, right? So this is where we end up getting this estimate. It's really from elliptic regularity, and then we get a functional calculus. Now the estimate follows from range of A being equal to L2 and on noting that zeta maps to zeta alpha e to the minus zeta is a psi-class function whenever mu is greater than omega. Okay? So then the quadratic estimates come from the quadratic estimates characterization of the H infinity functional calculus. Okay, so we're getting closer now. So this estimate is really of vital importance in what we're going to do. So now let's define H check of A d naught as being H minus A of H a half partial ME plus, so this is really an ansatz, right, that we're making. H minus a half partial M of E and H hat of A d naught is chi minus A star h minus a half partial me plus chi plus of a star h a half partial m of e. Okay. So what do we want to say about this? So what I want to first say is that this is reflexive. And the restriction of this to say smooth functions is equal to L2. Right? Okay, so now we can put all of our artillery together and prove this theorem quite easily, right? So we have already seen that the spaces H alpha M and H minus alpha M are reflexive. So this is reflexive with the restriction of this pairing to smooth functions being equal to the L2 inner product, right? We've already mentioned this. Okay. Now, we had a previous proposition since chi plus minus of A, chi plus minus of A star are bounded projectors on H alpha ME for all alpha in R, and the point is that we have chi plus minus A star is actually equal to chi plus minus A star with respect to this pairing, because they agree on L2, right? That's the main point. So the alpha equals 0 value is of course L2, right? Then we obtain that chi plus minus A H alpha, chi plus minus A star H minus alpha, reflexive and satisfying this condition, right? And satisfying the restriction equals the L2, right? This just comes out of the wash because it's already coming from a pre-existing reflexive pairing, which we know where this property is satisfied. Okay, and then the conclusion for H alpha A D naught and H hat A D naught follows. So maybe I'll leave that as an exercise to verify that, right? Okay, so that's one way to prove it quite easily from the pre-existing results. But let me just make a remark. So we could have proved this directly using that dom modulus A alpha equal to H alpha partial ME for for alpha at least positive, and for alpha negative, of course, we have this estimate, right? So minus alpha. Okay, so I should say that this is with the estimate A alpha of U is comparable to U H alpha. And for alpha below 0, what we have is a negative alpha of U is comparable to U H minus alpha. Okay, sorry, for alpha positive again, I've used the negative here. When U is in C infinity partial ME, or you could have U in L2 of partial ME. Okay? All right. Now we're cooking with gas. Okay. Now we're getting closer to what we want to really consider. All right. So now that we're armed with this fact, this is a very important fact, I'm going to present two lemmas. So recall, so again, recall that we have d naught equal to sigma naught partial t plus a. So that's if and only if sigma naught inverse d naught star is equal to minus partial t plus a adjoint. Okay, so consequently let's define E of U to be the heat semigroup of this, right? E of U is the solution operator to the heat equation with respect to the omega sectorial and invertible operator A, and then E star of U, let me define to be e to the minus t modulus A star of U for U in, so this is for U in L2 of partial M of V. Okay, so we've already considered semigroup theory and we've seen how this gives rise to semigroups. So lemma 1. For U in C infinity partial M of E, we have that E of U and E star of U is in dom d naught max. Oops. And we have E of U d naught is bounded by this norm of H check of A d naught, and we also have E star of U sigma naught inverse d naught star is bounded by U in H hat of A d naught. Okay, so these are really, so what's the goal here? So the goal eventually is to show that these check spaces I've written with respect to the operator A are really the check spaces. Okay, so it suffices to show, so for that we at least need to show that we need to show that the restriction operator then is a bounded map into this space, right? And if it's a bounded surjection into this space, then we know that we're in business. Okay, so we're just building up to that. So the first thing for the bounded part of the restriction map, the first thing we have to prove is this. Okay, so so let's first cut up the section U, the smooth section U, into the positive and negative spectral parts, right? So write u equals to chi plus a of u plus chi minus a of u. This is certainly true. And let's define them to be u plus u minus. So let's have a look at this first estimate. So this first estimate is e of u d naught. And what is that? So this is now going to be bounded by e of u. So this is linearity of the semigroup. So here, okay, so I should say here that we have to really keep in mind that the functional calculus now commutes, right? Remember, this was the last thing that I said in the functional calculus, that if an operator commutes with the resolvent, then it commutes with the functional calculus. So, but actually, in fact, this is not so necessary here. This is just linearity, but I just want to also make that remark. So first of all, we have this bound. So now let's consider, so let's hit this with the, so we have a differentiable, so the semigroup is differentiable. So let's have a look at what we get when we hit the extension operator with partial t. So this is going to be equal to partial t e to the minus t modulus a u plus minus, and this is going to be equal to negative modulus a e to the minus t modulus a u plus minus. Okay. And I also want to just note that a is equal to modulus a signum of a. Right, because the signum operator squares to 1. Okay, so modulus a is a signum of a signum a, but then a can be recovered as just taking the modulus and composing with the signum. Okay, so why do I want to know this? Because then I'm going to write the following. So now sigma naught partial t plus a of e to the minus t. So I'm going to look at the first expression here, right? So this is eu plus. So this eu plus is going to be equal to sigma naught partial t plus a e to the minus t modulus a u plus. And so this is going to be equal to sigma naught, and now we had the modulus a e to the minus t a u plus. And now I'm going to substitute this for modulus a. Okay, so maybe I should have written it directly in here actually. Right, so here let me write modulus a signum a. Right, so what is signum a? Let's just recall what signum a is. This is chi plus of a minus chi minus of a. Okay, so so now I have this signum of a e to the minus t modulus a u plus. So this is really where we need to note that the range of this e to the minus ta is again in chi plus. So chi minus kills it, right? So we're no longer left with this chi minus term in this second expression. And so that means that we get this to be equal to negative modulus a e to the minus t modulus a u plus. And then we get here plus modulus a e to the minus t modulus a u minus, u plus, sorry. So this is equal to 0. Okay, so since, I should say this, since e to the minus t modulus a u plus is equal to e to the minus t modulus a chi plus a u, which is equal to e to the minus modulus t chi plus a squared of u. It's an idempotent, and now I use the commutativity of the functional calculus to bring one of these chi's across, and then this is u plus, which tells us that this is now in chi plus of a of L2. Okay, so this is in the range of chi plus. And so if we hit this with chi minus, it becomes 0. Okay, so that's how we get this second part. So, so now let's have a look at the estimate that we need to make. So we have EU plus squared of D naught. So what is this term? So this is going to be equal to U plus of L2 of partial Z of E, right, squared, plus now we've seen we have a term here D naught of EU plus L2ZE squared, but this is 0 by what we've just shown, right? So we're only left with this term here. So what is this term? This is the term 0 to infinity of, sorry, there's an E here, right? So this is the term e to the minus t modulus A U plus L2 on the boundary dt. Right? This is just integrating slice-wise across the boundary. Right? So I think it's easy to verify. You can easily see that this is the L2 norm. Right? I hope that everyone's happy up to this stage that this is the L2 norm. Yes? So this is the cylinder. So this is partial m. So we first integrate here and then we integrate out to infinity. Okay? So so now what do we do? Well, now we look at this expression, and what we do is we insert a power t half here, and we also insert a modulus A half here, e to the minus t modulus A. But now this is again an operator that commutes with, so we've inserted an A modulus a half, which means we have to now balance this out by A minus a half, right? And we can do this because we assume that our operators were invertible to begin with. So let's take this squared, and now we've introduced a factor of t a half, so we have to cancel this out as well, so we get a factor of t minus a half, and we take this out of this expression, so we end up with an integral dt on t. Okay? So I hope maybe I should have been really clear on this. So maybe let me just really write this out to emphasize what I've done. So this is t minus a half, t a half. Modulus a half, modulus a minus a half. Right? Nothing magical here. So u plus squared d, so this is L2 partial me dt. That's the first thing. And now we just simply take this negative a half power out. We have this half here, e to the minus t modulus a, and now we have the a minus a half here, u plus squared L2 partial me, and now this is dt on t. But now remember the quadratic estimate that we proved in the last section, right? That's why we have to get this into this form, because now this is of the same form that we had before. This is t to the alpha, modulus a to the alpha, e to the minus t to some power, right? And some section, I don't know, this is just some section here, right? So now, because of the quadratic estimates, we obtained that this is precisely going to be comparable to modulus a minus a half of u plus squared. Okay, so this was from the theorem, right? Okay, so we get this, and so what is this exactly? This is exactly equal to, so I'll write it chi plus of a of u h minus a half squared. Okay? All right. Now let's look at the second estimate. Okay, so the inhomogeneous term introduces this negative a half term. All right. So I just want to also say here that where the power a to a half really comes in is because the quadratic estimates are really with respect to having t in the bottom here. Okay, so we couldn't have really, and because this is an L2 problem, we couldn't have really introduced another value of t here, right? So we couldn't have, this choice of a fraction of half is not an arbitrary choice. So now let's have a look at d naught EU minus, right? So we have to still take care of this other term. So this is going to be equal to sigma naught. Now we've seen before the first term is modulus a e to the minus t modulus a u minus, and in the second term what we get is, okay, so what we had was a signum of a e to the minus t modulus a u minus. But here this term, so this term is just going to be negative chi minus of a. Okay? So then we end up with sigma naught minus, so we end up with 2 sigma naught negative modulus a e to the minus t a of u minus. Right? This is what we end up with. Okay, so maybe I'll take the negative out the front here. Okay. So now when we want to compute the quadratic estimate, or the norm, the L2 norm, so EU minus of d naught squared. So as before, we have this term that we have to compute, which is, well, I'll just write the integral form out directly. So this is going to be e to the minus t a u naught squared L2 partial me plus, now I'm going to have to control this norm, right? So this is d naught of EU minus squared, and this is going to be L2 on the whole cylinder. But I want to first say that now we've already seen that this term, so we've seen that this term can be written as modulus a minus a half of u minus squared L2 partial me plus d naught EU minus squared L2 ze. But the point is that so we have the embedding that h half of partial me is embedded in h minus a half of partial me. Right? So at the level of estimates, that's saying that this first term is controlled by the, well, I should have just written h half here, right? So this is maybe a nicer way to write it. So this is going to be a h half of partial me. Okay? But now, sorry, h minus a half of partial me, but h half embeds, in fact, it's a compact embedding into h minus a half. So then this means that we get u minus a half, h half partial me, plus now we are left with having to estimate this second term, right? So what's the second term? The second term is, well, I'll just write this here, EU minus squared L2 ze. Okay, so let's now let's unravel this second term. So d naught EU minus squared L2 ze is precisely, again, 0 to infinity. Now we have, so I'll write, is comparable to, because I'm going to absorb this term in here, right? The constant and the sigma naught. So now we have to bound modulus a e to the minus t modulus a of u minus squared dt. So this is a boundary integral, sorry. This is an integral on the boundary, dt. So now what? Now we do the same trick as before, but now we've got this extra power of the operator a at hand. And again, we want to turn this into a quadratic estimate, right? Because that's really the critical regime. So when we want to convert this into a quadratic estimate, what we end up with is we introduce t a half, minus a half, t a half, and now we have a to a half here, e to the minus t modulus a. Now we have to take a power of a to a half to the u minus, L2 partial me dt. And now, as before, the t half comes out, so now we end up with the same quadratic estimate as before. with the power half, a half u minus squared L2me dt on t. But by the theorem, this is now going to be equivalent to a half u minus squared L2me. But what is this? This is exactly now the h half norm. Okay, so what have we proved? We've proved that E u minus d naught now squared is bounded by u minus h positive a half partial me. So if you put together the two estimates, so putting together 1 and 2, we obtain EU d naught is bounded now by u plus h minus a half partial me. Well, maybe I'll write it exactly in chi plus of au plus chi minus a of u h a half partial me. But this is exactly, right? This is exactly equivalent to the norm h check a d naught. Okay, so that's the proof of that statement. And so, okay, I should say for E star of u, sigma naught inverse d naught star u h hat a of d naught similar. Okay, so you can check that out if you want. Okay, so I think we have 15 minutes, so let me just go through the second lemma. So the second lemma now. Okay, so the second lemma. So again, this is for compactly supported smooths. So this is for, so I should have, okay. So this was for now compactly, for smooth sections on the boundary, right? So the E, the calligraphy E is really an extension operator, right? So what we've done is we've started with a smooth section on the boundary and we've extended it in some way into the maximal domain of the operator onto the interior. Now we want to go the other way. So to go the other way, what we want to do is we start with a compactly supported smooth section on the infinite cylinder, right? So for all compactly supported smooth sections, we have the restriction now to the boundary, measured in h check of a d naught, is bounded by u d naught, and u restricted to the boundary of h hat a of d naught is bounded by u sigma naught inverse d naught adjoint. Okay? So what's the proof of this? So let's recall first, so I've added this into a different section of the lecture notes, but let's recall the Green's formula. So the Green's formula says that for okay, so for u in C infinity C of ZE, and for V in C infinity C ZF, sorry, we have d naught uv minus u d naught formal adjoint v. This is equal to negative sigma naught u restricted to the boundary, v restricted to the boundary of L2 of M in F. Okay, so this is the Green's formula that we find. So unfortunately, I sort of skipped over this at earlier stages, but I guess it's not so hard to believe that we have such a Green's formula, right? And you can see now that if we take compactly supported smooth sections on the interior, this the right-hand term is 0. Okay, so now set V equal to sigma naught inverse star E star W, right? Where W is C infinity on the boundary of E, sorry. Okay, so we take E and then the sigma naught inverse star takes us back to F. Okay, so now with the aid of this formula, we get sigma naught inverse star E star of W minus U. So now we get sigma naught inverse D naught star, right? Because if we pull the D naught across, so okay, so I'll explain this in 1 second. E star of W, and this is now going to be equal to, so this is now equal to negative sigma naught U restricted to the boundary, and then sigma naught inverse star W restricted, okay, yeah, sigma naught W, right? Don't need to restrict to the boundary because we start automatically with something that's on the boundary. Okay? All right, so the point here is that this, it's not hard to check that this is precisely D dagger sigma naught inverse star. Okay, so now let's have a look at this left-hand term. So the left-hand term here, because we pull the adjoint across, this is precisely going to be U restricted to the boundary, W, L2 of partial ME, right? So here we're in F, L2 of partial M F, but we pull across and we get L2 of partial ME, right? So when we pull across by the adjoint. So what does this tell us? This tells us, so using this term here, what we get precisely is that U restricted to the boundary, W, is bounded by, okay, so we're just going to bound this by each of these terms. So we get sigma naught inverse D naught of U, right? So here I've pulled this sigma naught star across to the other side. E star of W, right? So these are now, so this is an L2 integral on the interior, right? So so maybe I should write that. So this is L2 ZE, and of course this is L2 ZF. Is it F? No, it's E. Okay. And plus, now we have this term U here, which is going to be L2 of partial ME. And now again, we have this, right? We have sigma naught inverse D naught star. So now, remember, this is also an operator mapping E to E. E star of W, L2 of partial ME. Okay. So, firstly, so what's this sigma naught inverse D naught of U? L2, well, I've written where it is. So this is now going to be bounded by, because this is a bounded endomorphism, right? just on each. So it's even though we're integrating this on the cylinder, this is just supreme and bounded, right? So because it's just acting on each boundary slice. So it's got t independent coefficients. That's what I'm trying to say. So because it's t independent coefficients, this is obviously bounded by d naught of u, which is now bounded by the operator norm, right? Which is strictly larger, since the inhomogeneous term is bounded by u d naught. Okay? Now, E star w, this object here, so the lower order term here, which is in the first integral again, so this is L2ZE, this is obviously now bounded by a similar argument against an operator norm, right? Any operator norm, in fact, because the operator norm contains the inhomogeneous term. Okay, so what does that yield? That yields for us that u restricted to the boundary of w, this is now controlled by u d naught against EW star sigma inverse d naught star. So both of them are controlled in this way, right? Because obviously this one is controlled by this obviously this one is controlled by this operator norm, because this contains the homogeneous part and this is the inhomogeneous part that gets controlled, and that's for the first consideration. And then we also have shown that this first term here is controlled by the d naught, and then the second term is also controlled by d naught, right? So both of these integrals we can control in this way. But now we have an estimate, right? So by the previous lemma, we have that this is estimated by w in h hat a of d naught. Okay, so this is the previous lemma, lemma 1. Okay. So what? So what does this win for us? This wins for us the following. So it shows us now, we divide through by this guy. So we have u, so let me write it out again, just in full detail. So what we've written is this, h hat of a d naught, is bounded now by u d naught. And this is for all w in C infinity partial m of e. But what is this? So if we now take a soup over this, right? So now take a soup. So by previous proposition, we have that h check of a of d naught and h check of a h hat of d naught. These are a perfect pair, right? This is a reflexive perfect pair. And we have C infinity of me dense in h, say minus h alpha partial me for all alpha in R. So so that implies that C infinity partial m of e is dense in h check a of d and h hat a of d, noughts. So that means that the norm u h hat a of d naught we can recover as a soup w in C infinity over the boundary, u restricted to here w okay, so sorry, this is u restricted to the boundary, divided by w h hat a d naught, which we just proved was bounded by u in d naught. Okay, so that's the proof. So the other estimate follows similarly. Okay, so this is why this perfect pairing business is extremely important. It allows us to reduce seemingly complicated things down to estimating against some nice dense subset with, for which we've already established we have some sort of perfect pair. And you can also see, you can also appreciate in this proof where L2 really plays a crucial role, right? So the point is that we really need to have this, we have this Green's formula, and on a nice dense subset, with respect to this Green's formula, what we see is an L2 inner product. And so everything now is really fixed by the geometry of L2. And then this geometry of L2 now goes into this into these perfect pairs, because we need these perfect pairs to be equal to L2 on a nice dense subset. Okay, so I think this is maybe a good place to leave it for today, and tomorrow we'll start with, not tomorrow, but next time we'll start with the theorem that establishes that these check spaces are in fact the check spaces that we care about, and yeah. Okay, thank you very much, and I'll.
Oh yeah, it's vacation. It's holiday.
Let me just send a mail out on Moodle, because I have no idea when holidays are and when they aren't.
Yeah, I think they are.
So it could be that we don't have a lecture on Monday, in which case we will meet on Wednesday. So any questions? So I'm sorry, we went through quite a few complicated things today, so I'm very happy to answer questions if there are any. No. Yeah. So maybe just to rehash, and if I could just take a couple of minutes, the point today was we understood the principle that we understood the spectral theory of the operator A by understanding the structure of its principal symbol. From that, we were able to use previous results to establish that it has a H-infinity functional calculus, and then we were able to prove these two fundamental estimates that we require that allow us to later, so we'll see that later these two lemmas allow us to assert that the boundary restriction map is a bounded surjection into this check space that we wrote down with respect to the operator A, right? The main point was that we have now cut up the check space into the, via this operator A and spectral subspaces of this operator A, so the thick and thin of it is that this, we know from considerations before that if we have a bounded surjection of the trace map, because its kernel is always dom d min, whatever space for which it has a bounded surjection, we have to have equivalent norms. So this tells us that this is the check space. Okay, so that's what we'll see next time. So we've fulfilled our goal, at least for the model operator, of understanding the check space purely in terms of some object that exists on the boundary. Okay, that's the guts of it. So thank you very much.